Then another attribute of the comparison of averages is the homogeneity of variances. So this is mainly the attribute of the unpaired sample t-test, or which are the unmatched sample t-test. So for that purpose, we need to assume that variances of the two samples are similar. So the general null hypothesis for this kind of the analysis of means is that two samples are drawn from populations with identical means and variances. So if the outcome of a test suggests the rejection of null hypothesis, then the possibility that it is due to difference in the variances should be eliminated. Because it is quite possible that if one of the samples, if one of the populations has a larger variance and the other population has a smaller variance, then it is quite possible that difference in their mean values is because of that difference in the variances. So therefore we need to make sure first that the difference between the mean values is not because of the variances. So we need to check for homogeneity of variances between the two samples before we actually apply the t-test for unmatched observations. So the variation in sample means will be greater than the variation due to random differences among individuals. So we need to make sure that this is not the case. So what we can do to check the homogeneity of variances, we can apply a simple test, and that test is called the f-test, and f-test is basically the comparison of variances. So it is applied before applying a test for differences in mean, and if the result of this test suggests variances are not similar, then a test for difference between means cannot be applied. So this is a pre-test that we need to do before doing the t-test for the unmatched observations, and we need to make sure that variances are similar. There is homogeneity of variances, but if the variances are not similar, then we cannot perform the t-test for unmatched observations. So this simple test needs to be done first. So what is the f-test? There are different types of the f-tests, and the f-test that we use before the t-test for unmatched observation is the two-tailed f-test. So this test assumes that the two populations with identical variances, they have a variance ratio of unity that is equal to 1. So when we say that the two values are equal, so if we are going to divide one value by the other, the answer should be 1, because if both values are same, the answer should be unity. The answer should be 1. For example, if we have value of 3 and the other value is also 3, then 3 by 3 is 1. If we have one value as 5, the other value is also 5, then their ratio is 1. So departure of sample variances from unity, that if they are different from 1, then it is supposed that this is because of the sampling error, right? So this is assumed that this is because of the sampling error. So we need to check that whether this is because of the sampling error or whether this difference is significant. We need to apply the f-test. So this is tested through a variance ratio or f-test, and this is the null hypothesis, and the null hypothesis says that the population variances are similar. The ratio of the population variances from the two samples is equal to 1. And the alternate hypothesis, this is the two-tailed hypothesis, and it suggests that the variance ratio is not equal to 1. Variance ratio of the two populations is not equal to 1. So this is the null hypothesis and the alternate hypothesis for the two-tailed f-test. And this is the formula for the calculation of f-test, that the numerator in this formula is the greater variance, which we label as sample number 1, and the denominator is the lesser variance, the value of the sample which has the lesser variance. So that is sample number 2, and this is taken in denominator. So we take this ratio and we check that whether this ratio is significantly different from 1 or no. So this is a simple formula of t-test. The degree of freedom for the f-test, we have 2 degrees of freedom because we have 2 samples. So V1 is the degree of freedom for the sample number 1 or numerator, and V2 is the degree of freedom for sample number 2, which is denominator. So we calculate 2 degrees of freedom. So we are taking one example, the 2 samples of limpets which are collected randomly on either side of an island. And the variable which is measured from these samples of limpets is the maximum shell length. These are the descriptive statistics for this data. So we have sample number 1, which is the west side, and sample number 2, which is the east side. So the number of observations on the west side is 41, on the east side is 31. The mean shell length from the west side is 24.71 millimeters, and the mean shell length from the east side is 19.6 millimeters. And then we have the standard deviation, which is 6.34 millimeters for the west side and 4.82 millimeters for the east side. And then we have the variance values, which is 40.1956 for the sample number 1 from west side and 23.2324 for sample number 2 from east side. And the degrees of freedom are 41 minus 140 and 31 minus 130. And this is our simple analysis. So you see how quickly this can be done if you have the descriptive statistics with you. So F is 40.1956 in this case, divided by 23.234, because remember the F test is the greater variance divided by the lesser variance. So greater variance in this case is 40 and the lesser variance in this case is 23. And when we divide that, the ratio is 1.73. So what should be the next step? To see if this calculated value is greater or less than the tabled value for the F test. So here we have the F distribution table at the probability level of 0.05. So all of these observations, they are at the probability level of 0.05, and you can see that there is V1 and there is V2. So in the columns we have a V1 distributed, and in the rows we have V2 distributed. And these are 2 pages because there are a large number of values. So on the other page also we have V1 and V2. Right? So what was our V1? It was 40 in this case, and what was our V2? It was 30. So our table value is 1.79, right? So we have our calculated value, which is 1.73, and we have our table value at probability 0.05, which is 1.79. So which one is greater? Our table value is greater. So our calculated value is less than the table value, therefore we are going to accept the null hypothesis. And the null hypothesis is that 2 samples have been drawn from 2 populations with equal or very similar variances. So this is the F test that we do. So after we are done with the F test, we may now proceed for a test for a significant difference in the mean values. So this is a pre-test that should be done before doing the t-test for unmasked observations. So if we accept the null hypothesis in this case, which means that variances are non-significantly different from each other, then we can proceed for the actual analysis of the difference in the mean values. So we have another example for the F test calculation. This is the dry weight in milligrams of leaves. And these are from 2 different fields, sample 1 and sample 2. So in the first field, the number of observations are 76. In the second field, the number of observations are 61. The mean dry weight of leaves is 84.33 milligrams from field 1 and 69.45 milligrams from field 2. And then we have the standard deviation, which is 5.84 milligrams from field 1 and 4.53 milligrams for field 2. And then the variance value, which is 34.55 milligrams from field 1 and 19.13 milligrams from field 2. So which one of these variances is greater? The variance from sample number 1, therefore we have labeled this sample as the sample number 1. And then we have the degrees of freedom, which is 75 for sample 1 and 60 for sample number 2. And then we do our calculation for the F test, which is 34.55 divided by 19.13, and we get our ratio as 1.8061. So this is our calculated value of the F test. Now consulting the F distribution table, our V1 is 75 and our V2 is 60, so our table value is 1.51. Now we compare the table and the calculated value. The table calculated value is 1.8 and the table value at probability 0.05 is 1.51. So here in this case our calculated value is greater than the tabled value. So what do we do with the null hypothesis? We accept it or reject it. So obviously we are going to reject the null hypothesis because the probability of null hypothesis to be true is less than 0.05. So therefore we are going to reject the null hypothesis, and we can say that two samples have been drawn from two populations with significantly unequal variances. So variances are significantly unequal, and these variances, they are not because of sampling error, rather rather they actually exist at the level of population. So because our variances are not same, our variance ratio is not equal to unity, so we should not proceed to test for a significant difference in the mean values. And now I want to show you an online calculator for the F critical value or the table value of F, and this is a web link for that online calculator. And this is how it looks like. So when you go into this web link, you'll find this calculator. So this calculator will tell you the critical value of the F distribution given the probability level, the numerator degrees of freedom, and the denominator degrees of freedom. So you just have to enter your necessary values and then click calculate. So we have these three boxes, so we have to fill these three boxes. So now the first input for V1, which is the degree of freedom of sample number 1, which is our numerator. So in the box 1 we are going to put in the value of V1. Then in the next box we are going to put in the value of V2, which is the degree of freedom of sample number 2, and this is the denominator. And remember, the sample number 2 or the denominator is the sample which has lesser variance. So this should be put in box number 2 of this calculator. Now we are going to put the desired level of probability, and it should not be greater than 0.05. So in box number 3 we are going to put in our desired level of probability, and because we are applying this F test to only check that whether the variances of the two populations that we are studying, that whether those variances are similar or no. So that is why we are just going to take the basic critical probability level, which is 0.05. So we cannot take the critical probability value greater than 0.05. So we are going to take the probability value of 0.05 against which we need to check our values, or we need to get the value of F distribution. So we are going to put 0.05 here. And now enter the values of V1, V2 and probability levels. For example, the degrees of freedom for sample number 1, 3, degree of freedom for sample number 2 is 5, and the probability level is 0.05. Now we press calculate and we get our results. So our result in this case 5.40945132, which is the table value of F for the degree of freedom V1 3 and degree of freedom V2 5 and probability level of 0.05. Right, so this is the table value of F, or the critical value of F at these degrees of freedom and probability level. And now we are entering the values from the example that we studied, and we studied the example of the shell length of limpets. So we are putting in the values. So what was our V1 in that example? V1 was 40, and what was our V2 was 30, and the probability level against which we checked was 0.05. So when we enter these values, what do we? So we get 1.79, and you can see that this is exactly the same value that we got from the F distribution table, right? So this is the value that we obtained. Now we put the values of the second example that we used. We used the example of the dry weight of leaves taken from two different fields. And what were our V1, V2, and the probability level? So our V1, the degree of freedom of the sample with greater variance, was 75, and V2, which is the degree of freedom for the sample with lesser variance, was 60. The probability level against which we are checking is 0.05, and when we calculate, we get the result, which is 1.50850109, and this is 1.51. And again, you can see that this is exactly the same value that we got from the table. So this is all for today's lecture, and in today's lecture we are starting the another series of the statistical analysis or statistical test, and this time we are focusing on the comparison of mean values, the comparison of averages. And we saw the general hypothesis for these kind of the tests. And what is the general hypothesis? General null hypothesis is that the samples have been drawn from populations with identical means, and the two-tailed alternate hypothesis is that the samples are drawn from populations with significantly different mean values, and the one-tailed alternate hypothesis is that in which we nominate one of the samples to have the greater value of mean as compared to the other sample. And then we saw some concepts and definitions, like we saw the concept of the matched and unmatched observations. So the matched observations are those in which the samples or the observations, they are taken from the same set of sample units, and the observations are taken twice and under different conditions or under different times. So these are the repeated measures. And then we saw the unmatched test. Unmatched tests are those in which the same variable is measured, that the similar type of the variable is measured from two different populations, from two different groups, and these two groups, they are unrelated to each other, and the observations, the sample units in these two groups, they are unrelated to each other. So they are not taken from the same samples. And then we saw that why it is important to have a test of homogeneity. But before that, we saw that the normal distribution, that it is a basic assumption of most of the tests which are used for the comparison of averages, that our data should be normally distributed. So we should have the normally distributed data so that we can have an accurate p-value, probability value. And then in the end, we saw that the homogeneity of variances is a requirement of the unmatched t-test, which is the test for the comparison of mean values in the unmatched observations. And this is checked through a simple test which is called as the F test, which is the variance ratio in which the greater variance is divided by the lesser variance, and then we compare the calculated value with the table value, with the critical value, and there we can see that if the variances of the two populations, they are significantly different from each other, or they are not significantly different from each other. So if they are similar, or if they are non-significantly different from each other, then we can proceed for the t-test for unmatched observations. But if they are not statistically similar to each other, then we should not proceed for the t-test for the comparison of averages. So this is all for today.